Yes.
Okay, fine. Let's start. So today I don't know how far we can do because internet is creating problem. Okay. Now we are in this slide. So last we are reading the LVDT. So linear variable differential transformer. And we are in this slide. So we said that this is an ideal utility where there is no loading effect. That means that the resistance of the meter is infinite and there is a single primary coil. There are two secondary coils, and yesterday I explained how the excitation voltage will be and how they will be inducing the voltage into coils based on the position of the core. So now from this, if we start writing the equations, circuit equations in electrical engineering sense, let's see what we can get. So let's consider the first primary. So primary, you see EEX is the excitation voltage. So and IPRP is the voltage drop on the resistance, and LPdIPdt is the voltage drop on the inductance. So we can write very easily that IPRP plus LPdIPdt minus EEX equals to 0. Now the voltage induced on the secondary is given by ES1 and ES2. So ES1 will be M1, the mutual inductance, and DIP, which is the current in the primary, DIP dt. And E1, 2 will be M2 DIP dt, where M1 and M2 are the mutual inductance, and this mutual inductance value depends on the core position. And then what we can write, the output ES will be the difference. I said that because it's the differential transformer, ES1 minus ES2. You see how it is connected, that that minus is connected with minus, so it will be subtracted. So it will be M1 minus M2 DIP dt. So now the M1 minus M2 is the net mutual inductance. And if you see this ES will be equals to M1 minus M2 DIP dt. And from there, if you replace the DIP dt, you will get ES or E0 as a function of EX. And you know that the net mutual inductance M1 minus M2 is the quantity that varies linearly with the core motion. Okay, as the core motion moves, that M1 and M2 changes. So ultimately M1 minus M2 is the quantity which varies. So E0 we could write from these two equations. From here it is M1 minus M2 DIP dt. From equation 4.23 you see that if we can write it, we shall write it like if I take the S transform, so IPRP plus LP S IP equals to EX. So if I take the IP, we can write it like this. E0 will be equals to M2, M1 minus M2 S, or D, they are writing D. You can write D or S, whatever you like. S by LP S plus RP into EX. So if you see this one, what you look, you see that it is a first order differential equation. So the transfer function order is 1, and because it has a 1 pole, but one thing you should recall that it has a 0 on the origin. Now, so E0 by EX, if you write what you are getting M1 minus M2 by RP into D by tau D plus 1. If you divide it by RP, so tau P will be equals to time constant of first order, and that is defined by LP by RP. So now if you see, this is a transfer function, and always it has a magnitude which has a phase always. So in the basic discussion of the measuring instrument in frequency response, I said that if the instrument can be represented with the help of a transfer function, and it has a magnitude which will vary with omega, it has a phase which will vary with omega. So if we write the magnitude and separate magnitude and phase part, what will be the magnitude? Magnitude will be the omega, because of 0 omega m1 minus m2 by rp, and denominator it will be omega tau p square plus 1 square root. That is very simple, because you take the mod of numerator, mod of denominator, you will get the magnitude, and then you will have a phi. What will be the phi? Suppose there is no d in the numerator, then the phase angle will be the tau minus tau tan inverse omega tau p. So, but now here we have a 0 on the numerator. So, 0 on the numerator will contribute 90 degree directly because it is 0 at origin. So, phi will be 90 minus tan inverse omega tau p. So, so you see that. So, what is the conclusion? Conclusion is that once we consider that LVDT as a zeroth order, as a ideal one, there is no loading effect, there is no current flowing through the meter of potential voltmeter where you are measuring the voltage. In such scenario, the LVDT will become a first order instrument which has a zero on at the point origin and which has a pole, and you see that the frequency response, that the expression for the magnitude plot of omega will be omega m1 minus m2 by rp divided by square root of omega tau p square plus 1. And what will be the phase angle of input output relationship will be 90 degree minus tan inverse omega p. 90 degree minus tan inverse omega p. Okay. So this is all about this. Now we'll come into it later. So if you see, this is a at omega, when omega is very small, then what will happen? Phi angle will be 90 degree, and omega is very large, tan inverse omega tau p, that will contribute to minus 90 degree. So phi angle will be 0. So phase angle will be always positive. So this is the LVDT transfer function and frequency response. So your homework will be, you plot the E0 by EX. You plot E0 by EX with respect to omega. You see how it is coming. So if you plot omega versus 20 log E0 by EX, you will see as there is a S on the beginning, from the starting point, there will be 20 dB per decade rise at the corner frequency, which is 1 by tau p. It another pole will contribute. So from there, the rise will stop. It will go with the parallel to x-axis. So basically, it will act as a high pass filter, because in the lower frequency it is cutting the frequency, attenuating, and phi will be 90 degree minus tan inverse omega tau p. Okay. So let's see if you have any query at this moment. Okay, as you have no query, let's proceed further. Attendance is very low. Around 29. Okay. Now, so for ideal case, we have derived it, and we have described how will be the transfer function, how will be the response of LVDT. Now let us consider a scenario. Okay, so still now we have assumed that no loading effect. It means that no current will flow through the voltage measuring device or the voltmeter, and as its resistance we consider as infinity. Now if we assume at a practical scenario where the resistance of the voltmeter or the voltage measuring device cannot be infinite, say let its resistance is Rm. So due to finite Rm, Is current, you see this one here, it's Is current. Earlier Is current was not flowing, but due to this one, Is current will flow through it. Okay. Then what will happen if Is current will flow? The primary side we can write. So then there will be the, due to Is current flowing in the secondary, there will be the voltage induced on the primary as well. So primary side we could write the voltage drop as IP RP like earlier, then LP DIP dt, or we can write LP DIP, or we can write LP SIP. Then the resultant mutual inductance is M1 minus M2. That's what I said. And there is a current which is changing with time, which is the secondary current. So the induced voltage to primary will be M1 minus M2 dSi by dt, or M1 minus M2 SSI or DSI, whatever, minus EX will be equal to 0. So that will be your primary side KVL. And now if you go to the secondary side, what you will be getting? So in the primary side, again you can write it that M1 minus MP d secondary side. Now if you write, what we are be getting, you are getting M1 minus M2 into dip dt, which is the induced voltage due to IP, plus RS plus RM. Total resistance is RS and the meter resistance is RM. RS plus RM into IS secondary, and then LS DIS dt, or LS D capital D IS, or LS capital S IS, whatever. So this 4.29 and 4.30, 4.29 is the primary side KVL, 4.30 is the secondary side KVL. Now if you can substitute uh, the IP you are getting from the 4.29 to 4.30, and then do manipulation, which is your homework. So equation 4.31, how do you reach from the above equation? This is your homework. And ultimately when you will read, you see that when you write, you will see that E0 by EX. So this you consider as a homework. Okay, so and it's very simple, 3-4 lines. So you will get numerator as Rm into M2 minus M1 into D, and the denominator you will get M1 minus M2 square plus LP into LS into D square plus some constant into D plus RS plus RM into RP. Here you have to substitute. uh, So here if you see this, what you are seeing, this expression becomes a second order transfer function. So the real LVDT, if you consider the ideal LVDT, it will be a first order system measuring device. If you consider a real IVDT when the loading effect is present, it will become a second order system. Okay. So at low frequency when phi tends to plus 90 degree, so at low frequency when phi tends to plus 90 degree, and at high frequency you see, so high frequency, because at low frequency all the pole will not contribute, only the zero will contribute, so it will be plus 90 degree contribution. At the low frequency, all the four, sorry, at high frequency. At low frequency, all the poles will not contribute, only zero will contribute, and there is a zero at origin, so you will get plus 90 degree phase shift. At very high frequency, all the pole will contribute, so you will have two poles, so 9 minus 90 minus 180 degree will be coming from pole, and plus 90 is coming from zero at origin. So at very high frequency, resultant phase you will get as a minus 90 degree. So the phase will change from plus 90 to minus 90. Okay. So at some frequency, the phase angle will be, so phase will change from plus 90 to minus 90. So at some frequency, the phase angle will be 0. So at some frequency, the phase angle will be 0. And we have to select the user. The user has to select that excitation frequency to avoid the phase shift. So again, I am coming. So from this transfer function, which is real LVDT transfer function, you see that it is a second order differential equation. It is a second order instrument. It has two poles and it has one zero at origin. So as it has one zero at origin at very low frequency, if the excitation frequency is very low, EEX, omega of EEX is very low, you will get plus 90 degree phase shift. If EEX is very omega of EX is very high, you will get minus 90 degree frequency phase shift, and we as a user want zero phase shift. So in between at some frequency, you will be having the zero phase shift, and you have to take that frequency of the excitation voltage EX. Okay, that is what I want to say. So the user has to select such excitation frequency so that the phase shift effect will be 0. So, and that will be the excitation frequency. Okay. Now, if you see that one figure, I showed you this one, and I said that later we are going to explain. So, if you see that xi is the x-axis and E0 mod is the y-axis. So as the xi will increase, that the m1 minus m2 will increase. So mod of E0 is going to increase. So, but it will not linearly, but it will not increase linearly always, because after sometimes it will try to fall little bit and it will become non-linear. Similarly, when xi is negative, this input displacement, then also the E0, as we are taking E0 mod, E0 will also rise. But what will happen that after sometimes it will also try to fall. So we will get, if the range whatever I said, if you work in this range, that means your xi input xi is in this range, then what you will get? You will get a kind of linear relationship xi versus e0, but it is not linear for the whole range. With that range where it is not linear, we will not consider. So for a limited input, which is our displacement, the output versus input relationship will be linear. Now another thing you could see that at xi is increasing, there will be positive phase, xi is negative, that is negative phase. So at xi origin, there will be 180-degree phase shift. Okay, because of the sign of the E0 is going to change. So ideally, output voltage should be 0. There are few considerations which you listen carefully. So you will not, in book also it is written, you can read the book also. So ideally output voltage should be 0 at null position. That is what we are showing. But due to stray capacitance between primary and secondary, and due to that, very small but non-zero null voltage is received. Okay, so that we have to offset, and there are procedure to offset so that the null voltage can be reduced to 0. Okay, this is one part. Next point I want to discuss, that output of LVDT is a sine wave. You know that we consider it a linear circuit. We are giving excitation with a sine wave, so output of the LVDT will be sine wave, whose amplitude is proportional to the core motion, that means displacement of the core. So if this output is applied to AC voltmeter, now you consider the measuring device. So suppose you are using the AC voltmeter, because output is AC sinusoidal. The meter reading can directly be calibrated. So meter will give you the RMS reading. So that reading can directly be calibrated in terms of, so calibrated means you can mark it in terms of the displacement xi, motion unit. Okay. So this arrangement is perfectly satisfactory for the measurement of static or slowly varying displacement. But there is a problem if the meter cannot. So there is a problem. Say the meter cannot sense the position of the core is above null or below null. What I mean to say. So now you can say that what is the displacement. So meter, it can be, you can mark it as a displacement, and above null and below null meter cannot say. That means if you are at null, you will give the 0 reading. If you at say some amount displaced on the positive, above null you will get some reading. If it is the same amount displaced from below null, you will get the same reading. So although you will know from the meter, you can calibrate it as a displacement, but you don't know whether it is above null or below null. Okay, this is a problem. So we need to have some circuit to know that above null or below null. Fine. Next thing is that the meter cannot follow very rapidly core position changing. Why meter cannot follow very rapidly core position changing? For rapidly core position, if it is changing, the output voltage as amplitude of it, that modulate the sine wave, and the demodulation is necessary. I'll come to it. So how little bit time varying voltage can be measured. Let's, before discussion, This point, let's leave it. Now tell me if you understand the previous point. So what are the points I mentioned? Let me summarize once again and let me see if you understand or not. So there are few points which I mentioned. What is that? I said that ideally output voltage should be zero at the null position, but there are stray capacitance. So due to that, output voltage remains some residual voltage, and there is some mechanism which is employed so that the output voltage is received to zero. This is the first point. What is the second point I mentioned? I mentioned that the output voltage is a sine wave and it is proportional to the core motion. So now, if the output voltage is applied to AC voltmeter, what will give the meter reading can directly be calibrated with the motion unit. So this arrangement is good and perfectly satisfactory, but there is some problem. First thing is that there are two problems. First thing is that, so even it is satisfactory for a very slowly moving, slowly varying displacement, not very rapidly varying displacement. There is some problem that the meter cannot sense the position of the core above null or below null. Okay, it is a big problem. So you have some displacement, the output voltage will show the displacement, but it cannot sense the displacement whether it is above null or below null. And then meter cannot follow the rapidly varying core position. These are the two issues. So for rapidly varying core position, the output voltage as amplitude modulated sine wave can be created, and then demodulation is necessary. We are coming, okay? Phase sensitive demodulation, something is necessary. We are coming to next slide to discuss something about that. Now you come to this slide. This is an interesting slide. Okay. Let's say we have an LVDT. Okay, we have an LVDT, and we are giving what is the input of the LVDT is the core movement displacement of the core. So Xi is the input of the LVDT. What is the output? Output is the E0 which you are recording on the AC voltmeter. Okay, that is the output. So E0 record. So if you see that the XY, now we consider the XY is changing. So you consider the case 1 where Xi is some positive, slowly varying, coming to 0 and then going above. Okay. And you consider another motion where the Xi is positive, slowly coming to null position and then going the below the null position. So for these two, what we can do, we will get the output of the LVDT. What will be the output? You will get the modulated sine wave. That's what I'm saying. So for varying thing, you can make it the modulated sine wave, you can get as output. So in the below, you see that from the LVDT, what you are getting a modulated sine wave. So irrespective of the core position above or null, because I said it cannot detect the core position above or null, so we will get the same output. Now the question is, from this same output, can we do some electronics manipulation so that we get the direction of the motion? So what we do, it is possible. So as the output is same coming out from the LVDT, what you can do the phase sensitive directly. If you apply it to voltmeter, it will not work. You can do is a phase sensitive demodulator. Both the cases you apply is a phase sensitive demodulator. Okay. So as you see that E0, the recording output is visually the same for the two different Xi. One Xi is from above null position to 0, then going above null position. Another Xi is above null position to 0, then going below null position. And E0 output is visually same from the two motions, coming out from the two motions. Now we apply the phase sensitive demodulator. If we apply the phase sensitive demodulator, what will happen? In one case, it will not come to 0 because it is a phase sensitive. It is doing demodulation and it is doing the phase sensitive. Okay, so it will not come below. And in another case where the Xi is going down below, you will get the sinusoidal modulated wave which is coming below the next plot. and then you apply the low pass filter. So if you apply the low pass filter, all these small sine waves cannot be taken, only its peak will be taken. So output you will get as the uh, positive coming 0, then positive. Again in the below case, if you apply the low pass filter, output will get positive coming 0, and then again negative coming negative. So ultimately the output can be replicated in the form of the input, which is the displacement. And this is the main point. So as I said that LVDT can measure the slowly varying input, and the output of it will be, we can make it as a modulated sine wave. And then if we apply the phase sensitive demodulator, then low pass filter, the LVDT output, the output coming out from the low pass filter will become a sensitive to the core position. So the above null or below null, how it is going with time varying, it can be detected. So this is all about the LVDT. Now tell me if you have any query up to this point. So we finish kind of LVDT, which is a very important displacement measuring device. Now tell me if you have any query. So if you don't have any query, let's proceed further. So we will read another displacement device, which is also very, very important and you are frequently encountering, which is called the encoder. Okay. So, so let's try to understand what do you mean by the encoder. This is also displacement measuring device. Okay. Now let me allow to give some introduction about the encoder. Then we will come to the construction detail and then the working principle. It's very interesting, very simple, but it is also very useful. So now, though a widely variety of linear or angular displacement or velocity measuring transducer we have seen. We have seen the potentiometer, we have seen the strain gauge, we have seen the LVDT, okay, the variety of all those things we have seen. But whatever we have seen, or the majority which exist, they provide an analog output. So what is the output coming out from the LVDT? It's definitely an analog output. What is the output coming out from the strain gauge? It's definitely an analog. What is the output coming from the potentiometer? It's definitely an analog. But now what is happening? This output, now we have always a computer inside a loop of measurement and control. So these output we need to feed to computer. Why? You will say why you need to feed to computer. The main thing is that that question I asked repeatedly in Viva also. So the main theme is that we need to feed it to the computer because we need to record it. We need to sometimes we need to take the control action based on this measuring device output. So we need to feed it to the computer. So computer register or computer memory, it should come the time versus the displacement. Now how we can feed it to the computer? Suppose there is no encoder, nothing. So how we can feed it to computer? So that was the question I was asking to Viva. So when you want to feed it to computer, you have to analog to digital converter. So the analog voltage you have to convert it to digital voltage, and then digital voltage you might have 8-bit, 16-bit, whatever you like. So then you have that many wires, and voltage of that many wires could be plus V or 0 like that. Then all the wires can be fed to computer either in the parallel port, through parallel port, or the serial port. Serial port and parallel port difference, you know, you have read the computer architecture. So you in desktop, generally in laptop there is no parallel port. So in desktop, you if you have a parallel port, so there are the wires, ports are there. So there you can connect those wires coming out for A to D converter, and then you have simple, I'm saying no data acquisition card till now. So and then you can run any program, any software, and you can read, you can write the code of the software, either MATLAB or C, whatever you want. that after some interval of time, you read the voltage at the parallel port, voltage of the parallel port. So once you read the voltage of the parallel port, it will give, suppose you have 8 wires. So which wire is 1, which wire is 0, that it can give. And based on that, you can convert digital to analog to know that what voltage is coming. And with the voltage, you can convert it, the physical parameters, what is the input. So, and if you, so in this case, whatever said, it is a very crude. And in this case, one problem will be there because you need to have run this sub code, and then after some interval code will check the parallel port, and it is not dedicated. Okay. So you cannot check very frequently. That means you cannot have a very uh, the frequency of the reading of the parallel port should be quite less. Suppose you want some gigahertz range refreshing rate or sampling time. You can call it as a sampling time because after that time you are reading it and restoring the data. Then it is not possible to use C or MATLAB program. So because it when you run the C or MATLAB program, computer is running its operating system and many other things. So whenever it will get time, then it will go and check it. So it may happen that your sampling time is very fast. So and in that time it is not possible to go to check because it is doing many other work. So you might sometimes need a very dedicated slot. Dedicated slot means dedicated hardware, uh, which we call the data acquisition system, which is DAC, DAQ. Okay, there are many types of DACs available in market. It ranges from few thousand rupees to even uh, half crore rupees, like that. Okay, so based on your need and based on your sampling time, you can select the data acquisition card. It is called the data acquisition card. There are dedicated computers, many companies prepared like LabVIEW, and so they have dedicated data acquisition card, and those computers are very costly and only built to make the data acquisition available. So these are all. So whatever be the case, now you can write a small code in C or MATLAB or Python, whatever you want to, and you give the parallel, you give the voltage in the parallel port. Suppose if you give the voltage 5 volt, 5 volt, 0 volt, 0 volt, 5 volt, 0 volt, like that, and then you read it and you see that whether you can read the parallel port correctly or not using this computer language. Okay, this is very simple. This is very simple task, and earlier days student used to do it in lab when the students are interested in reading and learning electrical stuff. In controller and lab, we used to give that type of small project. Now students are not interested. They used to say that we will not get job if we do control lab or if we do machine lab. And ultimately they are doing coding or something else. They are not interested. Okay. And by being not interested, they are eventually harming their career. Anyway, that is a different topic and debate. I will not go to that. You will know much better about your career than me. So the main takeaway, what I was trying to tell, that so till now, whatever we discuss, all the output is the analog output, and we cannot directly feed into the computer. That is the takeaway point. Okay. So if those are the analog output and we cannot directly feed into the computer, but computer is inevitable in these days in operate in measuring and in control loop. It has to be. Okay. So, and if we cannot feed it, so what do we need? We need to have a to D converter, which will convert analog to digital, and then digital voltage will be fed to the computer. Okay. So now A to D converter we need, and that output of A to D converter will go to computer. So the incorporation of A to D converter is required, and that is fine, except the penalty of cost. You need some cost associated because you are giving A to D converter, and it relates with the accuracy and reliability. But now we'll read one another displacement measuring device, which name is encoder. So it encoders are used to measure the position and the velocity, which gives directly digital output. Okay, you don't need to make the A to D converter, because the output of this encoder is itself digital. Okay, that is the beauty of the encoder, and that is what it is also much popular among the user. Okay, so what is the introductory thing? So I'm trying to summarize. In introduction, I discussed that most of the measuring devices are analog, giving output is the analog voltage, and computer is inevitable in the measurement loop or control loop. So you need to have one point of time those outputs are going inside the computer. So you need to have A to D converter, then it goes the computer through the parallel port or serial port. Now, encoder is such a device in which that A to D converter is not required. The output, the encoder also measures the position and velocity, both linear and angular. And the output itself is a digital. So you don't need A to D converter. Directly, the output of the encoder, you can feed into it. Now, encoders are mainly classified into two groups. Okay, now tell me if you have any query. Lot of time I speak. Okay, no question as such as of now. Okay, then proceed. Okay, now encoders are mainly classified into two groups. One is shaft encoder or rotary encoder, and another is linear encoder. Okay, so both the types, so encoders is mainly classified into two groups. First is the shaft encoder or rotary encoder, and second is the linear encoder. Among these two, shaft encoder is very popular. Again, both types of encoders are two basic types. First is absolute encoder, which measures the absolute position and velocity. And second type is the incremental encoder. Okay. So the shaft encoder or rotary encoder can be classified into two: absolute shaft encoder or incremental shaft encoder. Linear encoder is also classified into two: absolute linear encoder or incremental linear encoder. Further, based on the principle of operation, the encoder can be classified into two group. First is the optical encoder and second is that magnetic encoder. So among these two, again, magnetic encoder is not that popular. Optical encoder is very popular. Optical encoder is much more popular. Okay. So generally we use the optical encoder and we use generally the incremental encoder. Okay. Sometimes absolute encoder is used, but incremental encoder is also very popular. So if I come to the classification, the encoder is classified into two groups. First is shaft encoder and then linear encoder. And then shaft encoder or rotary encoder can be classified. Both the things can be classified absolute or incremental. Further, based on the principle of operation, it can be optical encoder or it can be magnetic encoder. Nowadays, we use optical encoder. It is very, very popular. Magnetic encoder, I personally never use. I don't think it is that much popular. Now let's come to the absolute encoder. So I said that encoder can be classified as the absolute encoder and the incremental encoder. So absolute encoder means what? So this encoder or sensor or this transducer provides what it provides. It will provide a digital output, okay, in the form of binary number, okay, where each binary code or binary number represents a unique position. Okay. What does it mean? Meaning that if sensor output so is the binary number, this binary number will be the unique position of either translational or rotational encoder. Okay. So now we are discussing the absolute encoder. So the absolute encoder, this sensor produces a digital output in the form of binary code, where each binary code or binary number represents a unique position. Means that the sensor output is a binary number which can be corresponds to a unique position, either translational or rotational. If translational, it will be in meter or something centimeter. If rotational, it will be in angle. So absolute encoder means this encoder provides the digital output which is related to the absolute position. Position means either theta or the linear position. This is the absolute input. And what about the incremental encoder? Incremental encoder will give the output, which is the incremental increase of position or velocity. So if we want to know the absolute thing from the incremental encoder, you need to know the first point properly, and that point you have to map with the absolute point, absolute position, and then the incremental output you will get, you have to keep on adding on the top of that point. Then you will get the absolute. So from incremental encoder, you can get the absolute values. You need to have reference and you need to keep on adding at each sampling time. Okay, that is the point. So this is, now we have to go to this figure, whatever I have shown. So I have to explain the construction. Let's see what's the time now. Oh, it's now 53. So next class I will start explaining this figure. So this is again will be going taking from the Dueblin. So all of you please read the Dueblin, and the attendance is very low. I don't know what the students are doing. Okay, so around 20 people are attending only. 75 is the class strength. It will be very difficult to see such low attendance. Anyway, if you have any query, you can ask. Otherwise, we can end here. We will start again from the uh, this encoder in Monday. Coming Monday. Coming Monday is not holiday, right? So coming Monday, 10 might be holiday or something. We'll see. So tomorrow is Deepavali, so Diwali. So you please uh, best wishes for such festival. You enjoy the festival. Okay. So today we end here. So we'll again meet on Monday next week. Okay. So thank you all of you and have a good day.